All right, chemistry. Today we're on to the second lesson in our thermochemistry unit, and it's on a subject called Hess's Law. So the enthalpy of reaction is the heat absorbed or released by a chemical reaction. The enthalpy of a chemical reaction is shown by placing delta H after the equation. So here's the combustion reaction for methane. You've seen this before. And when methane, 1 mole of methane is combusted, it releases 809.3 kilojoules of heat energy. This indicates that the combustion of CH4 is exothermic and releases 809.3 kilojoules of heat energy. Since exactly 1 mole of CH4 is combusted in this particular reaction, this also represents what is called the molar heat of reaction, the heat of reacting 1 mole of the substance. Hess's law is a method for calculating the enthalpy of a target reaction using the known enthalpies of other reactions. There are 3 rules to Hess's law. Rule number 1 is when a reaction is reversed, the sign on the enthalpy changes. So to create carbon dioxide from carbon and oxygen, that would be a synthesis or combination reaction. And what that would do is the carbon and the oxygen would then go to a lower energy state. They would be more comfortable together, and so they're going to release energy, and that's going to be 393.5 kilojoules of energy would be released to produce 1 mole of carbon dioxide. Now, if you wanted to decompose carbon dioxide into carbon and oxygen, go in the other direction, you would have to put in the exact same amount of energy, 393.5 kilojoules. So that would be an endothermic reaction to break apart carbon dioxide. The second rule is when the reaction is multiplied by a factor, a number, the enthalpy is multiplied by that same factor. So here, to make 1 mole of carbon dioxide would release 393.5 kilojoules. If you wanted to produce 2 moles of carbon dioxide, that would produce twice that many kilojoules. That's negative 787 kilojoules. Rule number 3, this is the one used at the end, is reactants and products can be added, that's on the same side of the arrow, and subtracted on opposite sides of the arrow. So let's take some fictitious reactants and products. Here we have A plus B produces product C plus D, and reactants 2B plus D plus 2C produces product E. So A and E only appear once, so they're going to appear in the final answer. The A is going to appear over on the left side of the arrow, and the E on the right side of the arrow. B and 2B appear on the left side of the arrow, so you can add those together. They're on the same side of the arrow, so they're going to add to become 3B, and that's going to be on the left side of the arrow. C on the right side of the first equation is subtracted from 2C on the left, leaving C on the left. In other words, the C is going to go on the side with the bigger of the C's. There's 2C on the left, 1 on the right, so it's going to become C, and it's going to be on the left side. So that would be your final equation that you would produce from these 2 equations up above. D, there's 1D on the left and 1D on the right, so they're going to cancel out. They would basically be subtracted from each other, so there won't be any D appearing in the final equation. Okay, so let's see a numeric example, and you'll do a couple of exercises. So let's determine the enthalpy for the following reaction. C2H6 plus 7/2 O2 produces 2 CO2 and 3 H2O. Now, you have to have the enthalpies of the reactions that you're going to use to create that. We call that the target equation. That's the one we're trying to create. So we have 3 known equations where the enthalpy is known. So the one we saw before is carbon plus oxygen produces CO2, has an enthalpy of reaction of negative 393.5 kilojoules. If you want to make 1 mole of water, you have H2 plus 1/2 O2 produces H2O, and that's going to release 285.8 kilojoules. Let me make a comment about the fractional coefficients here, up there in the O2 and down in equation 2 for the O2. And that is whenever, this is a special kind of reaction called an enthalpy of formation, which we're going to talk about in the next lesson. And whenever you do an enthalpy of formation reaction, it's always for 1 mole of what you're trying to create. So if you look at equation 2, you're trying to create H2O, and you're creating exactly 1 mole of it. In order to do that, you have to cut your oxygen molecule in half. It's the only time in chemistry where you can have fractional coefficients. So you can have a 1/2 O2 because you need half of an oxygen atom, that is to say half of an oxygen molecule, O2, to get 1 oxygen atom for H2O. H2O only requires 1 atom of oxygen. All right, so we'll talk about that a little more when we get to the enthalpy of formation. And then the third equation is you need 2 carbons and 3 H2s to form C2H6. So those are all balanced equations, and that will release 190.6 kilojoules. Okay, so let's go ahead and work through this. So first, what you're going to do, and this is the way I recommend you write it on your paper, is you rewrite the equations down below. So what you do is, first of all, you look for something in the target equation that only appears once in any of the 3 equations below if possible. And what we see is that CO2 appears in the target. It's on the right side of the arrow, and there are 2 moles of CO2 up in the target equation. So we look at the only equation of the 3 down below. There's only one that has CO2. And we see it has 1 CO2. There's only 1 mole of CO2. We need to make that 2. So what we're going to do is multiply equation 1 by 2. So that's going to double everything in equation 1. So we're going to have 2 carbon, and then we're going to have 2 O2s, and we're going to have 2 CO2s. So now our CO2s in the target equation matches up with our CO2s down there in equation 1A. So you renumber the equations so you keep track of them. So this is equation 1A. We've changed equation 1. We're going to call it equation 1A. And what we did is we multiplied everything by 2. So if you look at the enthalpy over on the right, it went from negative 393.5, it doubled, and it went to negative 787. Okay, now we're going to move on. And equation 2, we see that we have 3 H2Os up in the target equation over on the right side, 3 moles of H2O. And we see in equation 2 we have 1 mole of H2O. So we're going to want to multiply that by 3. Equation 2 gets multiplied by 3, so we can have 3 H2O over on the right. So that means everything gets multiplied by 3. So you have 3 H2, and now you have 1/2 O2 there, but when you multiply that by 3, you end up with 3/2 O2. And then the H2O, of course, gets multiplied by 3, and the enthalpy also gets multiplied by 3. So negative 285.8 up there in equation 2 becomes negative 857.4 kilojoules down in equation 2A. So now we have the 2 CO2 and the 3 H2O matching up on the right side of the target equation. And so now we're going to move on to equation 3. And what we see about equation 3 is it has C2H6, which is in our target. But in our target, it's on the left side of the arrow. And in equation 3, it's on the right side of the arrow. So we don't want to change the number of moles. It's the correct number of moles, 1 mole in both cases. But we're going to need to flip it around and put the C2H6 over on the left side of equation 3. So what we're going to then do is reverse equation 3. And there we go. So equation 3 got turned around. So the C2H6 is on the left, and the 2C and the 3H2s are on the right. So what that does is it changes the sign of the enthalpy. So in equation 3, it's negative 190.6 kilojoules. And in equation 3A, it's positive 190.6 kilojoules. So now we've done everything we need to do as far as that's concerned. Now we're ready to do step number 3, and that is to add these equations. Now we're done with equation 1, 2, and 3. We're not going to use those. Anything above that heavy black line we're not going to use anymore. We're only going to use the equations down at the bottom. So what we can see is we have 2c on the left of equation 1a and 2c on the right of equation 3a, so they totally cancel out. They subtract from each other. So they're not going to appear in the target, and if you look up at the target, you don't have carbon up there by itself. Next, the 3H2s on the left side of equation 2a cancel out with the 3H2 on the right side of 3a, and so you don't see any H2s alone up there in the target equation. So the only things we have left are the 2CO2 in equation 1a, and we see that appears in the target. The 3H2O in equation 2a also appears in the target, and the C2H6, 1 mole of C2H6 on the left side of the arrow, appears up in the left side of the target. So those three are all good. Now we have to deal with the oxygen. So if we look at oxygen, we have 2 O2s and on the left side of the arrow in equation 1a, and we have 3/2 O2 on the left side of the arrow in equation 2a. Now you have to do a little fraction math here. You have to get a common denominator. So 2 expressed with a denominator of 2 is 4 over 2. 2 is the same as 4 over 2. So you can take 4 over 2 plus 3 over 2, because they're both on the same side of the arrow, the left side, and add them up, and you get 7 over 2. There they are, and you see that that's up in the target equation, 7/2 O2. So now everything that's not in the target equation is canceled out. Everything that is up there in the final target equation. Okay, so we've matched up everything. Now what we do is we add up those enthalpies over there on the right, and that will give us the enthalpy of our target reaction. And when you do that, -787 plus -857.4 plus +190.6, add those up, and that gives you -1,454 kilojoules for the reaction. So we were able to figure out the enthalpy of an unknown reaction by taking the enthalpies of known reactions and combining those known reactions to produce that final enthalpy on the top. Now, you don't have to know how to figure out any of these reactions other than how to do the 3 steps. You're going to be given the equations 1, 2, and 3. You don't have to go and figure them out somehow. So you're given those. Now you got to figure out just how to manipulate them. Do you multiply them? Do you reverse them? How do you add them and subtract them at the end? Those 3 steps we talked about, that's all you would need to do, and that'll give you your final answer. All right, so that takes care of this lesson on Hess's Law. You'll get a few problems to practice on this, and that'll be our second lesson in thermochemistry.